In this video, I'm going to talk about heat transfer. So different methods for transferring heat from one object to another or one medium to another. So there are three ways for heat transfer to occur via temperature difference. And they're conduction, convection, and radiation. So that's what this section is going to be talking about. I'm going to talk about these three methods and what materials they occur in, because each of them occurs between different types of materials, and how they work. So just a reminder, how does heat flow naturally? You remember from previous videos, heat is going to flow naturally from hot objects to cool objects, or from hot media like air or water to cooler areas. So that's the natural flow. It always goes from hot to cold. How could you get it to flow the opposite way? You could get it to flow the opposite way if you do work. And so this is actually how refrigerators and freezers work. We're actually able to make refrigerators and freezers cold by applying energy. So we have to keep them plugged in and applying electricity in order to keep that energy going to reverse the energy flow, or I'm sorry, not the energy flow, the heat flow. Because normally it would want to go from hot to cold, so from the exterior area to the cold area and warm that up. So you need to do work, you need to apply energy in order to reverse heat flow. So we're going to start with conduction. So conduction occurs in solids and only in solids. It requires contact between the molecules. So it's the transfer of internal energy from molecule to molecule. And so you can see that down here in this picture if we look at what it looks like on the atomic level. So what we have over here, we've applied a flame to this pipe. And so you imagine these are the atoms in the pipe. The flame is down on this end. So the heat, the energy is being applied here. It gets these atoms really excited. They have lots of energy, so they start transferring that energy to their neighbors by vibrating, and it gets passed down the line. The energy doesn't go very far, right? Because it can only go so far, but the more energy, the more heat we apply here for the longer amount of time, the more of that energy that will get passed farther and farther down. And so that's how we can increase the temperature farther and farther down the material. Like I said, it requires direct physical contact to occur. So if you have two different solids, one hot, one cold, they have to come in contact with each other in order for the heat to transfer, in order to happen via conduction. So one of the things that we take advantage of as far as conduction goes with that physical contact is we are going to create insulation. So insulation, like if you think about the insulation like in your walls or in a cooler or something like that, it doesn't prevent or stop the flow of the internal energy. It doesn't prevent that heat energy from flowing through the object. What it does is it slows the rate that internal or heat energy flows. So what happens is it makes basically a pathway that energy has to travel through. That's because insulation contains air pockets. So again, if you think about if you've ever seen the insulation in walls or like the batting for blankets and coats, it's got lots of holes in it. So let me get my little pen out. And so let's think about this. We've got the two sides. Let's say this is like a blanket. And so these are the two pieces of the fabric on either side. And so we've got the batting in between. But that batting isn't solid, right? It's poofy. It's got the like polyester type material in between. and it's made up of strands that are all kind of locked together, but they're not solid. They've got spaces in between them. And what this does is it requires the heat to have to move along a longer path. So if the heat wants to travel through this blanket, so you've got heat on this side, right? Let's say like your body is against here. The heat comes and it gets transferred to this side of the fabric, and then it transfers in. But now if that heat wants to travel, it can't go straight through because it needs direct contact the entire time in order to travel. And it can't because of these air pockets. So it has to follow one of the fibers in the material. So it'll have to follow the fiber until it can get to the other side. So anytime it wants to do that, let's say this one's touching, oh, well, it can follow this one, and then it'll follow that one, and then it'll follow this one. And so that's why it slows the rate of that internal energy or heat flow, but it doesn't stop it. Those air pockets make the energy have to wiggle its way through. So, like I said, rock wool, fiberglass, those guys are going to help do this in like walls of a home. So it's going to slow that transfer of internal energy from a warm house to the cool exterior in the wintertime. And then in the summer, right, like right now, it's going to reverse. So right now it's hotter on the outside and cooler on the inside. So the heat is going to want to transfer into the house, and the insulation is going to slow that process so that not as much of that heat can make it into the house as quickly. So you've actually seen conduction occur, and you've seen the difference between areas that have insulation and areas that don't on buildings. If you've seen areas where it snowed, you get these patterns on the roofs. And that shows you areas where there's conduction directly happening and insulation. So the space where the snow is still there, that's an area where there's insulation. So the transfer is slowed down and the heat, the internal energy is not transferred as well. Versus where you've got the stripes are where the trusses are on the roof. And so it's a direct contact of the wood that's holding up the roof with the roof itself. And so the heat from the inside of the building can transfer straight through the wood out into the roof. And so that's why the snow melts in those patterns on the roof, because that's where the wood on the inside of the roof is directly in contact with the roof itself. So there's exactly what I just said. So the heat is being conducted from inside through that part of the roof. All right, so let's talk a little bit about good conductors, the materials that are good at doing this. So it's any material that has atoms with loose outer electrons. So the electrons can be bumped around and help transfer that heat energy. So examples of this are pretty much all the metals. All the metals are conductors to varying degrees. So some of them are better than others. And so if you look over at the table here, this gives you the rate of conduction of different materials. And so the farther up it is on the table here, the better it is at conducting heat. And so on our list here, silver is the best conductor, followed by copper, then aluminum, lead, or I'm sorry, iron, lead, and then concrete. So in this list, you can see that the top of the list is all metals. Then you're getting farther down. These guys down here are not quite as good. You can see that it says that they're better insulators. And we'll talk about that here in a second. So again, if you're doing different things that you need to be able to conduct heat, you're going to use metals. If you want to do things that are going to protect materials from heat, you're going to use our insulators. So they would be the poor conductors that delay the transfer of heat. Again, they don't stop it, but they delay it. So these are the good insulators. So examples would be the guys that we just saw on the previous slide. So let's go back and take a look at that. So the best ones are the ones down here at the bottom, a vacuum, and not the kind that we use to clean up. This would be a vacuum where there's nothing there, so like the vacuum of space. Or the one that we can create here is a vacuum where we remove everything from inside of a container. Air itself is one of the best insulators. That's why we use it in making spaces with our different insulators. You can see there's the glass wool or fiberglass. Styrofoam is plastic with a bunch of air blown into it. Then we get into things like cotton, wood, water, bricks, tile. You can see these are mostly things that we use for building. They're towards the middle. They're not as good of an insulator, but they're not great conductors either. So they can help insulate, but they're not as good at it. So why is the best insulator a vacuum? It's because there are no molecules. Remember, conduction only works with direct contact because it moves molecules. And so if there are no molecules to move, you can't transfer the heat via conduction. And so that's why, as far as insulators go, a vacuum is going to be your best insulator. So there are some other ones. Ceramic is another one. If you've ever come across some different tools and so forth, ceramic is a common insulator against heat as well. So conduction, I'll put this video link in with the lesson. So I don't know how many of you are familiar with coal walking. It is an activity that is commonly done in certain parts of the world. When I took my physics class in college, we had some people who would set these demonstrations up. And they are very cool and they are pretty impressive. There is some danger to them, and they'll talk about that in the video. But they are, if they're done correctly, generally safe because of poor conduction. And so you can watch the video that will be linked to this that'll explain why it is that you can actually walk on hot coals and not get harmed. All right, so that's conduction. The next video is going to be on convection and radiation.